Okay. Very first thing, GNU Parallel installation. Oh, what did? Oh, I think I clicked on a link accidentally. Go back. Huh. Oh, I think I need to scroll up. No. All right, well, this is fine. Anyway, GNU Parallel, it's just a 14,000 line Perl script. Almost every operating system is going to come with like just a user bin Perl environment. This is something that you can just get the file, put it in your path, and be able to use it. So that's the site. That's also the place to find sort of the documentation and every little detail on all of the sort of flags and parameters. Although I'm not going to go broad, I'm going to focus on stuff that's useful and then point out some things to look out for. So yeah, you download the BZ2, you decompress it, you put it in your path. There are also official packages available providing GNU Parallel for a lot of different platforms. So you yum install Parallel and whatever version happens to be the operating system you're using. If you're working on a system that is administrated by someone else, there is some likelihood that it will already be installed, maybe in the RPMs on the system, maybe made available as like module load parallel. We used to do that at NERSC, and then I got it added to the RPM, so now it's just available by default. Yeah. Okay. All right. So once you've got it, what is it? The one sentence description is GNU Parallel uses a template that you write to assemble shell commands and run them in parallel. One of my favorite aspects of GNU Parallel, it is very clear about what it is not. So it is giving you a very strong clue about what roles in the construction of your workflow you should use it for versus what things you absolutely need something else for. It takes no responsibility for the ordering that the commands that you give it run. It will tend to run them in order. That's just the tendency, but it's not something you should count on. You shouldn't program anything against it. Just assume that they will be out of order and you won't be unpleasantly surprised. It takes no responsibility for interacting with multiple nodes or schedulers or MPI. It has no Slurm integration. It has no understanding of communicators or the presence of other nodes. It is on one node and it can dispatch work to any of the cores that are on that one node. All right. So straight into the simplest possible example. There's a parallel command. The command that it is turning into sort of the repeated thing to run in parallel is an echo. There's a string there, and then that 3: operator, that is the simplest possible way to send tasks to GNU Parallel. So you separate some strings by spaces, you put them after those 3 colons. Each one of those strings will be turned into a task. GNU Parallel will run one echo command for each one of those. The curly brackets are the location where the task string gets substituted. And then the output is sort of that constructed string there. And so there's 5 tasks run, each one substituted a different number in. It is possible to combine these colon operators to get sort of the product of all of those options. So if you have 2 3: operators, each with its own list of strings behind it, it will take every combination of pairs and send that to the substitution brackets to be given to the command. So you can do sort of this cross product thing and get more commands overall. That's useful for, say, if you're building a nested directory structure or navigating one. you can run, each of your sort of payload commands inside these different directories that are in the other list. And then another operator that you can add here, the plus sign after one of these colon operators, that changes it to act like a dot product. So instead of every combination, it will consume items from the list in the order they come. So if there's 2 items in both lists, then it will just sort of match 1 to 1, and you'll only get 2 tasks run in parallel using the plus command in this instance. So the reason that I believe GNU Parallel is sort of the most accessible workflow tool is because you can do one-liners in it that are not like they're comprehensible to a regular person. It's not like Perl mumbo jumbo that does real useful work. I need 100 folders because I'm planning on ingesting some data that is on 100 experiments. GNU Parallel, make dir brackets, colon, 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 sequence 1 to 1,000, there it is. Another thing that's you can do in a one-liner like this, so if you evaluate an ls command, giving you every directory folder inside a thing, each one of those will become one task, and the name of that will be passed to the brackets in GNU Parallel, and that can be used to run a piece of analysis on every single file in a directory, and you just did it with one command line. Okay. The next operator is the 4 colon list source. So the 3 colon list source, you give it a space separated or otherwise separated list of strings, and each one turns into a task. 4 colons are for opening a file, and each line in that file will be your task. So the example that I'm showing here, I'm actually mashing together several of the things that I've mentioned so far. We've got an initial list that is generating strings 1 to 100. A second list that is coming out of what's in tasks.txt, and it's got the plus operator. And so what this will do is this will append the number to whatever content was in tasks.txt, and so you'll be sort of adding a count as you go along when you're substituting in the curly brackets. And so this tasks.txt happens to have 6, 7, 8 in it. And so it's added the 1, 2, and 3. The plus operator will stop when either of the lists is exhausted. So that's the reason that you don't see any of the numbers coming out of the seek from 4 to 100. They just sort of got ignored because it ran out of things to count. Other options to get the content out of files and into your task list, you can redirect standard input. You can use a pipe operator. That's especially useful for like chaining together a find command and a grep and maybe something else to filter things. And the ultimate result is sort of a narrower subset of tasks that you want to actually give to your parallel command. And also there is a file wildcard operator that you can use with the 3 colon argument. So if you put star.txt, then everything in the working directory that ends with .txt will be turned into a task string and given to GNU Parallel. Okay. The second part about GNU Parallel that is really nice is the substitution modifiers and the control that gives you over manipulating paths and file names and extensions, and sort of the bones and meat of getting the correct files from wherever they start out into a task list and into the application that you're parallelizing. So some of the options that are available, you can add a dot and you can remove the file extension from something. You can remove the directory path from the front. You can remove the file name and extension and be left with just the directory path. And you can add a dot and a slash to get only the base file name and get rid of the extension and the directory. So all of sort of the pieces that you need to cut out a specific part of a path that may be appearing in task list and move that piece onto your payload application. The # will give you a task number. And so that just counts from the first thing Parallel sees is 1, the second thing it sees is 2, on and on and on until your list of input tasks is exhausted. And then the last one here, number here is, substitute that for an integer. If you have an input that is somehow column separated, maybe you've got multiple colon operators. In that case, each one of them counts as a column. Or maybe you're using a column separate flag and you give it a comma or something. And that will also divide the input strings into columns. And then you can select specific columns for substitution into your command. So if you're doing something like a parameter sweep and you've got a file that's a CSV with all the different combinations of parameters you want to do, but there's a little bit of extra sort of, you've got to put the flag in that accepts the particular parameter for your application. This is a convenient way to cut out those pieces and give them to the correct flag as you run your application. So example, getting your task from a CSV file. So there's the example there of the file. There are 3 columns. There's names, numbers, and then plants. Pipeline doesn't really fit through, but my examples get weirder as we go on. The parallel command adds the column separate flag, sets it to a comma. So now you're splitting each one of these into a column. And then the echo is using just the first and the third column. So it's ignoring those numbers in the middle. And the output of that is it's picked out the numbers and it's only keeping the names and the fruit. Now, a warning pitfall to stick out here. GNU Parallel does have a CSV flag, which will do the same thing. The trick is that it depends on a Perl module, text CSV parse, something like that, that is not necessarily in a Perl installation. Like it's not present on Perlmutter. And if you didn't have it, you would need to go to CPAN to get that module to get it. So my suggestion is just use column separate instead of trying to use that CSV flag. Okay. Many tasks inside a single node job. Now we're expanding to dealing with the batch scheduler, reserving actual compute, like not just running on a login node or an interactive shell. And how can we utilize Parallel in those situations? So in this example, we just have one node. So we don't have to worry about Parallel not being good at interacting with other nodes. It's just the one node. And we just want to send our list of input tasks to it. So the batch script gets the reservation, one node, a short little bit of time, the parallel command, the payload command and the argument that it takes, and then the input string. But everything else is pretty much just as simple as I've only added the Slurm infrastructure. Everything else can be the same. The one bit that is new here is this jobs flag. The jobs flag for Parallel is telling it, this is the most concurrent processes that I want you to launch. So if your application, if you know how many threads it uses, and you know how many cores are on the node, then you can do the little bit of math and you can set the jobs yourself, and that sort of rate limiting to not overextend the resources can be done by parallel. Great. And this will work for anyone. Just replace payload.shell with your application and sort of whatever constructions you need with task substitutions to get your parameters and arguments right. Okay. The next example. So we're gonna pretend that our application is an MPI application, and we're gonna have multiple nodes. One of the limitations is that MPI applications have to be set in motion by a launcher of some sort. At NERSC on Perlmutter, it's srun. For OpenMPI, it's MPI run. I don't know any of the others off the top of my head. But that has to be sort of the component that sits right in front of whatever your MPI application is. Oh, that was it. Okay. Okay. Now I've got my bearings again. In the past, we have had trouble at NERSC from a user anti-pattern that basically write a bash for loop and put an srun in and launch a bunch of applications. The trouble with that is that the Slurm controller, and there's just one of them managing the entire cluster, and the database that it uses to keep track of state on the system, that is a limited resource that can be overwhelmed. So when 1,000 sruns come in over the course of a few seconds, all those remote calls will suddenly churn up all the threads, the database log, everything on the Slurm controller. And then you lose responsiveness from everyone else on the system. So then your SQs and your S accounts and your S batches don't return quickly because the Slurm controller is busy processing 1,000 sruns. So to combat that effect, the first sort of new change here is the use of the delay flag. The delay flag is telling Parallel, wait 3 seconds between every parallel launch. You're probably not going to be running tasks that need only a few seconds to run, at least on the order of minutes or hours or whatever. So that delay ends up being sort of small in the grand scheme of things, and you'll be able to populate all the nodes. If you do need to run a bunch of tasks that only need 5 or 10 seconds, then you probably should be doing something else. Okay. Limited the number of jobs to 4. So the srun has been moved inside the parallel. The parallel is doing this command to the Slurm controller, sort of setting up the number of cores and the number of tasks per each launch of this MPI application. And then this piece here, the distribution equals block pack. So this came up in a ticket that I worked on about a month ago. Someone wanted to run a high throughput workload. The application they only had access to MPI scaling to threads. It didn't have OpenMP or any other threading thing. And their optimal run was 6 MPI processes per application. But we've got hundreds of cores on each node. So in order to actually use that effectively, you've got to have a lot of these 6 core processes running at the same time. But the other thing that you want to look out for is you want to make sure that they stay on the same node all of those processes. The default Slurm behavior, because it's expecting something that looks like an HPC workload that's shaped completely different. If you have two nodes and you give it a MPI process that has two MPI procs in it, it will put one on each node. It'll split it apart, and you'll end up with that network hop in between instead of doing just sort of memory access if those two processes had been on the same node. So the purpose of this distribution block and pack command is telling Slurm, no, don't do your default assignment of procs to nodes. What I want you to do is pick one node, put all of the things for a job on that node until you fill it up, and then move on to the next node. And this way, out of the 50 MPI applications, small MPI applications that are running, amongst 2 or 3 or whatever nodes, none of them get split across the network. They're all localized to an individual node, and you can still have your good throughput that way. Okay. And the last thing to point out special in this case, this network equals no VNI. This is, this is specific to particular machines. It may be an HPE Shasta specific thing or OS or something. It may be a Slingshot specific. Slingshot is the name of our high-speed network. The VNI is a resource that Slurm tracks as it's allocating jobs that roughly maps to network adapters. Our compute nodes have a limited number of network adapters, 2 or 4. So if you've got 6 core MPI processes, like tiny little things, and you tell srun to assign to it, without this flag, srun will also assign one of the VNI resources to it. So you'll get one process on a node, you'll get a second, you'll get a third, you'll get a fourth. But the fourth one, that's the last network adapter allocated. And then Slurm thinks, okay, this node is out of resources, and it moves on to the next node. So you end up with 200 empty cores on that node where otherwise things would have run fine. Okay. And then there's kind of a, well, look at this from a higher elevation. Why are you using parallel and not using a bash loop with a sleep inside or something like that? Why not do the simple thing that you might be more familiar with? Well, one of the things that's obnoxious to try and do is backgrounding multiple sruns. If you are running lots of small MPI tasks, then each srun is going to need the ampersand on the back to keep it alive while that's running and get focus back to launch more of them. And then you have to add a few more flags to your job to make sure that, say, if one of those ends early, it doesn't cancel the entire job, because one of the HPC assumptions is that if you lose a node in your job, or if you lose a process in your job, because it's assuming that everything is a tightly coupled MPI process, it assumes, oh, this must be a total loss. I should cancel the whole thing and send it back. So you might lose an entire job early because one of your processes ended early, and it cancels everything else that hasn't done yet, where that otherwise would have been perfectly viable compute. And another thing that's a benefit here, the capabilities of Parallel to build command lines and argument lists with substitution operators, it's a lot easier to use and convenient and more powerful than trying to write just srun lines and patch things together that way. You have a lot more flexibility in, customizing file path names or arguments or that sort of thing. That's harder to do with just plain bash. Okay. What sorts of things might you see go wrong if you're trying to use GNU Parallel at large scale? Uh, so the first one, and I saw this myself when I was trying to get, my test was trying to get as many blasts running with as high throughput as possible over multiple nodes. This was on Cori when we had the burst buffer. So I was replicating multiple genomes for the reference data on the burst buffer and also running tons and tons and tons of parallel blasts, like even more than the number of cores because the bottleneck is IO and not compute. But each one of those runs is under the hood using some temporary file handles. So it is possible if you have a lot of GNU Parallel tasks in flight at the same time, you might run out of file handles. You'll hit the U limit and get a message to that effect. And in that case, you're maybe you can raise the U limit. There is a little flexibility there in some systems, but you're probably better off just trying to figure out a different way to, maybe break your parallel down into 2 or 3 runs, run fewer at the same time, but maybe you can give them some more cores so it's not a total loss. But yeah, you pretty much need to make less stuff running in parallel as possible to get around that. Another thing that can go wrong, say you're using file path wildcards in your task ingestion. If you've got a really large directory, then that wildcard is going to expand to an extremely long command line, and you may hit a limit on arguments list too long. Depending on what your command is in your payload, some things like RM, sort of basic commands that can accept 1 argument or 2 arguments or 3 arguments or an indefinite number. You can add this X flag and GNU Parallel will smartly distribute your tasks such that they get close to that limit for an argument list. And then it cuts that off, sets it running as a task, and it starts a new one. So it doesn't go over that argument list. But your payload has to be flexible enough to allow that arbitrary number of arguments. If it's sort of a meteor application that doesn't, it's got to be 1 argument at a time or something like that, then you won't be able to. And in that case, you just have to find a way to subdivide your very large number of parallel runs into smaller pieces that don't go over the limit. Like, maybe you can use awk to do a round robin thing so that 1 parallel gets all the even ones, the other gets all the odd ones. Maybe you can sort of grab half of it in one side and half on the other. Something to break apart the big block into some smaller blocks. Traps. So when I mentioned earlier that sometimes workflow tools will have features that may sound good and it seems like what you want, but actually there's something that doesn't quite work hidden. Or it's something that doesn't fit the role of that tool, but everybody wants to be all things to all people. These are those sorts of things in GNU Parallel. And I suggest avoiding them and choosing another tool if you have a need that sounds like one of these would solve. First, GNU Parallel has an SSH flag. And the way that works is you give it a host name or a number of host names, and when it's launching processes, it will SSH to that node and set those things running. This does get you access to multiple nodes. And it also does so that it's able to load balance between nodes to some amount. Like if one of these jobs is very long and it fills up a node a long time, as it's assigning more SSH ones, it will go to the other nodes that become available sooner. The problem with this is the capability, the strength of the pipe going to all of these SSH destinations is pretty narrow. If you try to run more than tens, maybe 100 processes in parallel, regardless of how many other nodes there are, you max out the capacity of your head node that's running parallel and launching these SSH to actually send the communications to launch and run these things. So you end up with sort of a sloping performance where adding more and more things in parallel just don't get to the nodes fast enough. And you max out your capacity. And I guess from the perspective of an HPC person, only being able to scale to tens or 100 of concurrent processes isn't particularly good, and you really should choose something else, something srun, some other arrangement of your bash. Okay, GNU Parallel is Perl. There are a number of ways that the arguments for GNU Parallel can ingest Perl regular expressions. I worked in bioinformatics stuff before Python became popular, and I did a bunch of Perl. And Perl regular expressions are cool and they're powerful, but they're not readable. I bet there's a fair number of people, especially younger people, that have not learned to read, to work with these things. And if you set up a system and you pass it off to someone that inherits from you, they will probably be annoyed when they look at what you're doing and see that there's a regular expression there. And they've got to, go do some Stack Overflow from 15 years ago to try and figure out what's actually happening in that regular expression. Okay, another set of flags. There are SQL master and worker flags available in GNU Parallel. When I first saw those and imagined what I would do, I imagined that there was some capability in there to use the database to store state information. Maybe it's tracking if a task is completed or not. Maybe if it's tracking if a task has already been assigned to a worker, if it's available. And then, this would be great because then I could run parallels on different nodes. They could connect to the same database and it would all be synchronized. But that's not how it's implemented. How it's implemented is that the database just stores exactly the same information as the task list that you might put in from a file. There's no state information or tracking if something is running or not. So you can't use it to, synchronize workloads amongst multiple parallel instances. And so for the additional cost of either having an SQLite sitting around on the file system or even like a Postgres containing your job information, you don't actually gain any new capability relative to having a file with all your tasks in it. If you do want capabilities like that, you should choose a different tool that does use its database to store state and synchronization information. Okay. And this is sort of the pinnacle example that I have to show for trying to make GNU Parallel work in a high performance computing environment. So presume that you have lots of tasks, not MPI, in your entire workload, and you want to run it on a large allocation of nodes. You can do that with GNU Parallel. Oh. So this is broken down into a couple different scripts. At the top level is the driver that has the Slurm allocation information. So I'm getting 2 nodes. I'm telling it I want 1 task per node. I'm running an srun, and I'm using the srun to fan out parallel calls so that there's 1 parallel running on each node in my allocation. So it's like launching an MPI process, except I ignore the MPI part. Because when you launch an MPI process, you're getting copies of your application running in the particular arrangement on different nodes you want, but it's also passing like environment information so that they can all connect to the communicator. This, I just ignore the communicator. I don't care about that. I just want a parallel running there. So so those two extra flags that I've added there. The no kill flag is telling Slurm, if one of the nodes in my job dies, don't kill the job. Don't worry about it. Just keep the other things running. And that way, if you do happen to lose a node due to a crash during your job, you won't lose the entire job. You only use that one bit of what happened to run on that single node. Okay, and the weight equals 0. Another default, because we assume it's MPI behavior, is that when one of the processes launched by srun ends, Slurm assumes that something's gone wrong or you're done. And so it cancels all the rest of them and ends your job allocation. If your load is not balanced evenly, which would almost certainly be the case, one of your parallels is going to run out of work before the others. And you don't want that to be the point that your job ends. You want everybody to get a chance to finish. Okay. So the second script. So this script is taking care of assigning tasks to each of the parallels. Each node has its own parallel. And the requirement that you have for getting this right is you want every task to be assigned to exactly one node and not any of the other nodes, so that completely unique work is being given to all of the parallels running on each of the nodes, and you're not duplicating any effort. So the presumption here is that the $1 has your task input list, and that's being put into awk. And the setup of awk here is using a round robin distribution to statically assign all of your input tasks to individual nodes based on sort of a modulus operator of how many nodes there are. So first task goes to first node, second task goes to second node, third task goes to third node until you get to all your nodes, and then it starts back over. So this is using Slurm environment variables that have been populated by srun. Srun is telling you there are this many nodes in your entire job. That's part of the modulus arithmetic. And it's telling you which node out of those nodes you are. And that's the other half of the modulus. Okay. Yeah, and then that just gets piped into the parallel. So each one is getting that trimmed down and isolated task list as you go to the payload. And the payload is whatever your application is and whatever your argument list needs are as far as actually doing substitutions to get the correct thing. So this is sort of the limit of what I would say is reasonable for using parallel on high performance computing. Like this is pushing the boundary of what's reasonable. Like not everybody wants to have to understand an awk script to get this running and the explanation for what's happening. If you need this, you may very well want to choose a different tool that is able to interact with Slurm to distribute work to multiple nodes. Something that requires more setup, but you get that extra capability, and that makes something like this easier. There are some drawbacks to doing it this way that other things would be able to do better. For instance, load balancing. Because the assignment of tasks to nodes is static, you will probably have more work end up on some nodes than other unless every single task is exactly the same length. But even then, like the number of tasks might not evenly divide the number of nodes or something like that. You could potentially have load balancing problems that GNU Parallel would not be able to do anything about. You can't use this method if you have an MPI application. And the reason for that is because you can't nest srun commands. Because I've already used an srun at the very beginning to distribute the parallel commands to all the different nodes, none of those can run an srun or launch an MPI application. So this would absolutely not work if you were trying to do many tasks that were MPI tasks across a long thing. You would end up doing something, you might do okay with the previous example that was MPI tasks for multiple nodes, but you're limited to the rate that a single parallel can issue tasks in that case. Yeah, less intuitive and readable. This is another case where if somebody inherits the script from you, they may have questions about what is going on with this awk statement. Need to devote some extra thinking capacity to figure out what's going on instead of something you can just look at and decode quickly what's going on.